All right, let's say we have a data that consists of the first vertical row consisting of time units from 1 to 3, and each of these sets of time units sampling the same individual. So given this data here, what we call is a panel data that consists of cross-sectional units with, again, given time, a consistent time measurement here, a set of time units that samples the same individuals. If it does that, if the time units are consistent, and it samples the same individuals, and so then that's what we call a panel data. So this is just an example of what I put. I just put the names of the sampled individuals. And to the right, you can kind of see that the whole reason why we would do that is to still find the relationship between x and y. In this case, two x's. So just generally speaking, when we're describing a panel data, if our vertical length given by time is relatively long, we'll say that the panel data is we'll say the panel data is long, whereas if we don't have if the vertical length of the time is short, then we'll say the time is short. Whereas if you look at the horizontal length here, if that part of the panel data is very long, then we'll call it wide. And in contrast, if it's relatively short compared to the vertical part of the data, then we'll say it's narrow. All right. So just like similar to a panel data, the pooled regression model, what we call the regression model for the panel data. It will look something like this. Now, the only thing different is that these x variables represent the specific individuals and time. And so notice how each of these variables has a specific time and then a specific unit to it. And that's what this is representing, the individual and then the time. All right. So for this kind of stuff of the panel data stuff to work, we have to make assumptions. Excuse me. So for the pooled least squares to work, we have to be able to minimize the errors. The expectation of errors must be 0. The variance must be homoscedastic. The data cannot have correlation. So the covariance of an error of one individual to another, or an error of one time to another, cannot be related. And of course, it cannot have endogeneity. So we can't have any confounding variables, no Granger causality problem, no omitted variable problem, stuff like that. Pretty much similar to the assumptions we made in the past. We see very similar patterns of it, and we should, because this is pretty much the same data that, it's pretty similar to a time series model, except the only thing we're doing is we're making consistent time cross-sectional units across the same sampled individuals. So when we regress this function on a panel data, it will assume that these slope coefficients, right here, beta 2, beta 3, they are actually identical for all units in this case, Nathan, Sam, and Luke. And as you can already tell, that's pretty unrealistic and restrictive, which is why we have alternatives to the to the pooled regression. But when we simply just regress this function as a pooled regression or as an ordinary regression, we kind of have to assume that these coefficients are applying to all of these units. And okay, so how to correct for heteroscedasticity? Pretty much the same. We'll call this the cluster panel robust standard errors, which is a special unique solution for panel data, but we'll test it. We'll correct it on the software using just kind of the similar process as what we did before on a regular data set. All right, so now we get to alternative methods of the pooled regression. So we'll what we call is a fixed effect that captures the individual or behavioral differences of what we call individual heterogeneity. And so normally in like a pooled regression, the differences between the individuals, because these coefficients assume that the slopes for the individuals are the same, regularly the difference captured by individuals is only by the intercept. So not the slope, but only the intercept. So like Nathan, Sam, Luke might have different starting points, but we all assume they have a similar behavior. So that's what a pooled regression does. But what the fixed effect model will do, or the FEM, what they'll do is it's basically saying, hey, we have these individual or time differences that, over time or over different individuals, their behavior is actually different, which is pretty much realistic to what will be typically analyzed in a data set, because if it's the same, then you kind of lose meaning of analyzing the data set. All right, and so what the fixed effect model is doing is saying, so it's saying that there are differences within individuals. And so when let's say we're only accounting for the difference of the individuals, then we must consider the characteristics that are indifferent to time, because if we measure characteristics that are also affected by time, then we don't know if the differences are caused by the individual behaviors or the time changes. And so just for individual differences, we have to measure time invariant characteristics such as race and gender and height. Height mostly, that doesn't change, but I guess in adolescence it can change. And so there are two main methods of measuring this FEM. It was what we call the use of least squared dummy variables, and then the typical fixed effect estimator. So with the addition of dummy variables, it will look something like this, where we include a dummy variable for every variable. So obviously the characteristic has to be binary. So if we're measuring like if someone is shorter, if someone is what gender someone is, or if they're short or tall, or if they're slim or big, so anything like that. We have our dummy variables here, and then we also have our regular coefficients here. And so we're just adding onto the dummy variables that are included in part of our regression, like right here, whatever that might be. So if like x1 or x2 is a dummy variable, then we might do something like that. When we're regressing this function, we always have to make sure that we exclude one dummy variable, because we do that to avoid multicollinearity. Now the proof of this isn't necessarily clear, nor do I have it, but it's kind of similar to how we subtract a couple numbers from the sample size to obtain the degrees of freedom. All right, so going into this function further, the intercept is given by the level of y when all of these are 0. So when the dummy variables are 0, when the x variables are 0, this coefficient is when this dummy variable is 1, whatever that may be, and that's the change in the second individual's output in relation to the first individual. And then this regular beta 2 is not part of the dummy variables, so that's just applying to all individuals, not just the dummy variables here. All right, and in order to test if these dummy variables are effective or not, we can use, again, what we call the f-test. So in our null, we'll say these dummy variable coefficients are not significant, and that because they're 0, we can just use the pooled since these individual characteristics are not relevant. Whereas the alternative is saying, these coefficients are significant and we need to include them in the model. All right, so that's what we do for individual differences. So if it's, if the x variables are like gender and height and time invariant variables that doesn't change over time. But if we have x variables that we think can consider over time, like let's say grades or specific preferences like elastic products that we might prefer over some time, but if they get more expensive, then we might decide not to buy it, anything like that. Then we should also account for that. And the way we do that is we still use the fixed effect estimator to account for those time differences. Now, if we think if there are both time and individual characteristics that might account for this data that would not make it a pooled data. So if there's like gender and male gender, which is a time invariant variable, and then like grades, which is a time dependent variable, then we'll use the two-way fixed estimator, which accounts for both time and time invariant characteristics. And so the way it fixes for time is it will average this regression function over time by dividing by t, and then it will subtract these values from the mean to obtain those differences. So that's how it mathematically obtains those heterogeneous values. All right, so the way we count kind of what we call the sample size or the degrees of freedom in a panel data is not the most simple. The formula I gave here is the way we determine how much data or sample size we have, given by n times t minus n minus k. And so the n is represented by the type of individuals. So we have, just in here, we have Nathan, Sam, and Luke. So we'll call n equals 3 because we have 3 different individuals. Each individual has a time set unit of 3 units. And then we have 2 coefficients, so k equals 2. And so with using all that together, we have n equals 3. Time for each unit is 3 units, so 3 times 3, minus 3, n, and then minus the number of coefficients 2. So we actually only have 4 observations when it comes to just this panel data alone. Which would kind of make sense because just looking over here, it would, a lot of times we would subtract 1 from the degrees of freedom. So we have, we might exclude like the first Nathan, Sam, and Luke. And then we also might exclude some of these n's because we have 2 unknown variables. So obviously the main point is that we usually want a larger sampled, like when we're sampling Nathan and Sam and Luke, we want a longer time sample, more than 3, and we want, more individuals rather than just Nathan, Sam, and Luke. All right, finally, going back to the pooled and fixed model comparison, the way we calculate the F statistic for testing the fixed model is given this function here, where it should look pretty similar, but the degrees of freedom obviously is different for the panel data, and so the denominator will look a little different, and then the sum of squared errors for the restricted and unrestricted will be given by the restricted being the pooled and the unrestricted being the fixed effect, because the pooled is saying that the function is, these individuals, sorry, not this one, but the one right here, these coefficients are the same over individuals, or the same over the same over time. And that's pretty restrictive of what we see. It's very limited, whereas the fixed effect model allows for some heterogeneity because we must account for those differences that might come into play over these Nathan, Sam, and Luke, of what they might prefer differently or how they might act differently over time. Okay, I'm going to stop it there. In the next video, I'm going to go over random effects, which also end up interacting with pooled and then the fixed effect. And then I'm going to go over the hypothesis test to determine which of the three is, of how we determine which of the three is ideal for the panel data.